video, I'm going to be going through the 2012 trial question 12, and this is a three-force method question. So this is relevant for year 11s. Even though it's a truss, I haven't included the inside of the truss because it's not necessary to be able to do this part of the question, right? So you'll have to, as part of the question, be able to find the internal members. We're not interested in this. In this case, we're just looking for the reactions. Now, if you ever have a question that has a beam or a truss, this is really for year 12s. If you're looking at a truss that has two reactions and one external force, you should be thinking three-force method. So the question is, first of all, are these forces parallel? Let's just ignore this force because this one here is unknown. Are those two forces parallel? No? So if they're not parallel, that means all three forces must be concurrent. We know there's a third force here, RR. Now normally we would think about RR as being RR vertical and RR horizontal. In this case, we're just going to treat RR as its combined value. So the first thing we need to do is we say, well, if these are concurrent, where are they going to be concurrent? So I'm going to draw and extend this line. Oh, a little too high. Okay, and then this one here. And I've now found my point of concurrency. I label this as OMG POC. That's just a tradition from where I first started teaching. Samson tells me it's also the name of his car. But anyway, we've found the point of concurrency. Now what we need to do is we need to find the angle of this third one. So what we're going to do is from that point of concurrency, we're going to find this angle, because this third force also has to join up from this dot to that point of concurrency. This third force has to meet that point of concurrency. We obviously know the point is being applied here, so that is going to give us the correct angle, which we can measure. Because I have a protractor, I can now solve this in one of two different ways. So I've got my angle, and I'm going to measure this, and let me get my protractor. Look at that for my safe problem. Oh, what do you know? It's 36 degrees. Actually, my diagram was perfectly to scale, so it wasn't. But we're going to say I found an angle of 36 degrees. So what am I going to do now? Now that I have these three forces, what I'm going to do is I'm going to draw a vector diagram, and I've run out of space a little bit, so we'll have to try and squash it in. Who would have thought drawing such a big diagram would cause problems for me? But what I could also do is I could say, well, I already know this value here to be correct. I already know this value here to be correct, and it's already drawn to scale. And I can then find this one, I can just draw it on the paper. I could say, well, if I know this is 100, I can just draw that out. But I'm not going to do that, I'm going to do it here. I'm going to say, I'm going to just draw it here. And I'm going to say this value, I'm going to call that value 100. And then, with this here, I'm going to draw this line so they're now at the correct angles, at 60 and 45 degrees. And then, using my protractor, or I could just slide this line across, I can draw this angle here. So I'm going to take my protractor, and we said it's 36 degrees. It's out there. We can make a vector triangle that looks like this. So if this is 100, we've been told that this is 100, I'm going to write that in now again, 100 kilonewtons. If that's 100 kilonewtons, at this scale, well, this is actually going to be pretty close to 100 kilonewtons. Now the question is, I've already drawn the arrow as going this way, but I want to remind you that if this is going relative to this dot, if I know that this force is 100 kilonewtons, if it's going in that direction, they all need to be going in that same sense. This one here is going anti-clockwise, so they all must be going anti-clockwise in order to maintain that tip-to-tail connection. So that one's about 100, and then I'm going to measure this one and say, at this scale, I don't know, it looks like it's about 40 kilonewtons. Okay, let's say I don't like that method, right? Lots of people don't like to do things graphically. That's fine. If you don't like to do it graphically, what are the other alternatives that you can use? Well, if you know the angles, yeah, okay, so if you know the angles, what we can do is we can measure things. We can say, well, if this is 36 degrees, then this here is going to be 45 plus 36 degrees. What's that angle going to be? What's that angle? 45 plus 36 is what? 81? Does that sound right?
1620. Wait, sorry, I did times.
Okay, so that's 81. But the other angles we've kind of got to measure, like we've got to measure these other angles. And so if you know that, can't believe I'm getting my protractor out. Let's say I want to find this angle here. For those of you who have been in my class, you know that I very seldomly use a protractor. Especially this one is so big that it makes it really, really, really hard to see the values. And I'm kind of guessing anyway.
24. It'd be 36 minus.
Does anyone have like a regular sized protractor?
Yeah.
Pass. So I've worked this out on paper. I can't actually see the camera. So I'm going to call that angle 76.
Yeah.
So what I can do here is if I know that this is 100, I can say that this is my unknown. What's this one here? This one here is RR. I can say that RR, which is unknown, equals sine 70 over RR over sine 76 equals 100 times over sine 81. I can then multiply both sides by sine 76, crossing out this, and say that RR equals 100 sine 76 divided by sine 81. If I type that into the calculator, (100 sine 76 divided by sine 81 equals 97. Oh, it's pretty close to my answer.